Do you see the figure? What are the two components in floating point representation?
The mantis and the exponent.
Yes. What is the range value of mantissa? Range of values of mantissa? What is the range of M? I am showing you the slide.
Sir, 0 to 16.
0 to 16.
No, sir, no, sir. That was in different representation. Here it will be 1 to 1 by 2, sir. 1 by 2 to 1, sir, in this. It is in different
Yes.
representation.
So 1 by 2 to 1, it is in decimal, but in binary it is from 0.1 to 0.1 is more than or equal to 0.1 and less than 1. Okay. With sign bit. So we have considered one number, let us say 5. Okay. So we represent it as mantissa 0.101. Okay. Because 5 represent 101 in fixed point 101.0. Okay. And in fixed point it is 101.0, but in mantissa first part, that is mantissa, and other part is exponent. So in mantissa it will be 0.101 and it will be multiplied with exponent part. That will tell you where the binary point would be. So in mantissa, binary point is at first after the sign bit, that is 0. 0 is the sign bit. Positive, it represents positive, and after that the binary point exists. But actually the binary point should lie just 3 points after that. So that means after 101. So your exponent should be such that it will designate, it will tell where the binary point should be. So that means after 3 points, after 3 bits. So that's why the exponent should be 2 to the power 3. Okay, 2 to the power 3, but you cannot represent 2 to the power 3 decimal. You have to use some binary storage structure. So in the exponents parts, it should be 0, 1, 1. That means it is 3 plus 3. Okay, 0, 1, 1. So whole 5, number 5 is represented as 0.101 in mantissa, and exponent it is 0, 1, 1. So there are all total 7 bits. 1, 2, 3, 4, 5, 6, 7. So all total 7 bits represents here the floating point representation for 5 bit for number 5. Now similarly for number 3 by 8. Okay? 3 by 8 is what? In fixed point. In fixed point it is 0.011. Okay? 0.011 simply. But your mantissa should be 0.11. Okay? Anyhow you have to, because mantissa is greater than 0.1. So you take mantissa as 0.11, then you shift the binary point left. How much left? It is 1.1 digit left. Your mantissa is 0.11. To make it 0.011, you have to shift the binary point left by 1 digit, but it is negative shift or left shift. Okay, so that means it is 2 to the power minus 1. If it is positive shift, right shift, then it would be positive 2 to the power plus something like in the earlier case 2 to the power 3. So that moves the binary point right of 3 digits, and here binary points left, movement left by 1 digit. So the exponent should be minus 1. Okay, and minus 1 is represented as 101. Here also again sign bit is there in exponent part. So the leftmost bit LSB represent negative and 01 is the magnitude. So the number 3 by 8 in floating point represented as 0.11101. Then we talked about multiplication of two numbers. The example is 5 by 5 into 3 by 8. So the general law is that both the mantissa would be multiplied but exponent will be added. So exponents are 3 and minus 1, okay, that we have seen for the two numbers. And so that means you have to add this plus 3 and minus 1 in 2's complement. It is subtraction. Okay, it is subtraction. So in 2's complement, no subtraction is used, only addition. What is the advantage of 2's complement? That no after subtraction is required. If you add it, then it will behave as subtraction. So both positive and negative numbers are added. So positive number is 3 and negative number is minus 1. So you have to represent minus 1 in 2's complement. So it is 111 and plus 3 is 011. So we get 010, okay, in 2's complement. 2's complement it represents plus 2. Okay, positive number indeed. 010 is the sign bit and 10 is the magnitude. So this is the exponent part. Then for multiplication of these two numbers 101, the mantissa, then mantissa will be multiplied. So you see that after multiplication mantissa becomes 0.01110. Okay, so 6-bit format. If you consider 6-bit format, this is the mantissa. Now we write the whole number, that is 0.01110 into 2 to the power 010. Now you can shift the binary point by changing the exponent. If you want to shift the binary point right, then reduce the exponent by 1. So 010 is now becomes 001. Okay, so this way it is done. Now what about addition? Addition of two floating points. There are two numbers 5 and 3 by 8, where mantissa is 0.101 for 5 and exponent is 2 to the power 3, and for the mantissa 2, okay, is 0.11 and exponent is 2 to the power minus 1. So for multiplication of this such two numbers where exponents are different, okay, so you have to make the exponent same. So let us make it same as 2 to the power one number, that is 2 to the power 3. So 2 to the power minus 1 should be converted to 2 to the power 3. by multiplying it 2 to the power 4. Okay, so that means multiplication of 2 to the power 4 means shifting, you are increasing the exponent. Okay, so you have to decrease the mantissa. So that means it would be binary point would be shifted left. Okay, binary point would be shifted left, so that both will become 2 to the power 3. Left movement by how many bits? By 4 bits. So for the second number 3 by 8, mantissa becomes 0.000011. So if you then add these two, it will become 0.101011 into 2 to the power 11011. It represents plus 3. Okay, 2 to the power plus 3. I hope it is clear.
Yes, sir.
Okay. Then some analysis. Now look, read the lines. Suppose uh, we shift the second number by 5 bits. Okay, what will happen? Second number means M2. We shift it by 5 bits, left shift. So the number would be 0.000001. So you see that there is a loss of data. Okay. Earlier the number was 0.000011. All total say it is 6 bit. Okay, in the magnitude part of the mantissa, 6 bit. But if there is a shift of 5 bits, okay, then 1 bits will be lost. So this is, and even after if you shift it by 6 bits, then it will be all total 0. So the number that was actual number, now it got erroneous. Okay. So this is one problem. Okay. You see that it should be observed that the shifting operation required to equalize the exponent of x2 with that of x1 results in loss of precision. In this example of the 6-bit mantissa, let us say the mantissa bits are 6, excluding the sign bit. In this example, the 6-bit mantissa was sufficiently long to accommodate a shift of 4 bits to the right for M2 without dropping any of the ones. So here we have shifted, actually we have shifted the binary points left, but mantissa is shifting right. Okay. So if there is shift of 4 bit, there is no problem, no loss of 1. But if 5 bits are shifted, then there is a loss of one single bit. And a shift of 6 bits to the right would have resulted in a mantissa of M2 that is 0.000000. Okay. Unless we round upward after shifting, so that this one M2 is equal to 0.000001. So this is one problem, that if your word size or bit size is limited, then further if you change the exponent, then there is maybe loss, and there may be overflow also. Okay, if exponents, the sum of exponent exceeds the dynamic range of the fixed point representation of the exponent. So if the exponent number of bits in the exponent is also limited, okay? So if after adding of these two exponents causes the increase of bit, then there will be also problem. Okay. So here one particular case is considered. Okay. Let us of the here fixed point and floating point have been compared. So let us see from with this example, okay, that if we have a computer with a word size of 32 bits, it is possible to represent 2 to the power 32 numbers. Okay, to 32 bits are there, so we can represent it 2 to the power 32 bits, including 0. Okay. So if we wish to represent the positive integers beginning with 0, the largest possible integer that can be accommodated as 2 to the power 32 minus 1. That is 4294. This is a long digit number. Okay. Now this is the largest number for 32 bit storage. Now the distance between successive numbers, the resolution is 1 because each number is changed by 1 bit. Successive number is changed, there is change of 1 bit in each success number. Means the LSB is changing. Alternatively, we can designate the leftmost bit. Now if you consider the negative numbers, if we can designate the leftmost bit as the sign bit and use the remaining 31 bits for the magnitude, so in such case, fixed point representation allows us to cover the range minus 2 to the power 31, 2 to the power 31 minus 1, whose value is this, 2 to the power 31 minus 1. Okay. So from negative numbers to positive maximum, lowest number to highest number. If you consider signed bit representation, okay, or fixed point, these are the smallest and largest number, both in negative and positive sides. Okay. Again with resolution of 1.
Sir, excuse me, sir.
Yes. Yes.
At one place, -1 will not be there, no, sir. Generally, we'll have 2 power minus 2 power 31 to 2 power 31 minus 1, like that.
Hmm. What you are asking?
No, sir, I was saying if we include 0 also, then if we
Yes.
do -1 2 times, and one more bit will be missing, no, sir. So only one time -1 will come for the range.
Hmm. No, see here, if you consider the sign bit system, okay, that for that this is the range, no? So leftmost bit is the sign bit. So you do not have to consider that bits.
Yes, sir, got it.
So then, so this is one case. Suppose let us consider one smaller value. Suppose we have one numbers plus 7, okay, and your bit is number of bit is 4. So how will represent plus 7?
So it's 0 1 1 1.
0 1 1 1. Okay, so that means it is what, 2 to the power 3 minus 1, isn't it? So excluding the sign bit is 1 and remaining 3 bits is magnitude. So we have to consider only the magnitude, 2 to the power 3 minus 1. Okay, that is 7 plus 7. Then how will represent minus 7?
Sir, all ones.
All 1. So that's why it means it is minus for the plus this 1 for negative, then also 2 to the power 3 minus 1, isn't it? So
Yes.
that's why the range is this way, that minus 2 to the power 31 minus 1 to this 2 to the power 31 minus 1. So now another issue is that if you, so this was the issue for integer numbers. Okay. Now if you consider the fractional number, so your word length is fixed. So let us say word length is 32, where one bit is for sign. So remaining 31 bits are used for its magnitude. And out of this 31, let us keep it 21 bits for integer and 10 bits for fraction, like 111.111, like that. Okay. For example, if it is 6-bit magnitude, so your number say would be 111.111. Okay, either positive or negative, means before this, if it is 1, then it is negative, and before this, if it is 0, then if it is positive. So in that case, what should be the range? Okay, so lowest number is minus 2 to the power 31 minus 1. This is the magnitude. That would be multiplied by 2 to the power minus 10. Okay. So because 10 bits is for fraction, we are not using all 31 bits as magnitude. We are out of 31, we are using 10 bits for fraction, 21 bits for magnitude. So if you see that, if you calculate the series, okay, so it will, after the series, after the using that formula for series, if you go on solving that, it will come like this. Okay. 2 to the power 31 minus 1, 2 to the power minus 10. So it is to be 2 to the power 21 minus 2 to the power minus 10. This is the negative side, and the positive side, the same value, 2 to the power 31 minus 1 into 2 to the power minus 10. So and its number is now, it has become this one, okay, minus 2 to plus 2 something. Okay. So So in this case, the resolution is 2 to the power minus 10. Why this resolution? Can you tell? The resolution is 2 to the
Sir,
power minus 10.
two integers, there are two minus 10 fractions.
Yes, fraction is there are 10 bits fractions. In fraction parts, there are 10 bits. So 1 by 2 to the power 10. Okay. So that's why the resolution is means the change of 1 bit in fraction. Okay. Change of 1 bit in fraction represents this value. Okay. So uh, suppose your number is 0.111. Okay. Then next number is 0.110. So the most right bit is changed by 1. So due to that, the value, the smallest change, that is the smallest change in the number. So that is 2 to the power minus 10. But the dynamic range is the resolution. So resolution is increased a lot. Earlier, the resolution was 1 bit only. Okay. The distance between successive numbers is only 1 earlier in the case of positive, in the case of integer number. But in the case of fractional number, now resolution has been increased, okay, by this much factor to the power minus 10. But dynamic range is decreased. Earlier dynamic range was this one point minus this one. I don't know how much it is. 2000 lakhs of 21 lakhs, more than this very high value. So how many digits? There are 3, 6, 10 digits. Now here 3, 7 digits. 7 digits magnitude number. And here also in both negative and positive. Now it has its magnitude has become lesser, but also dynamic range. So the dynamic range means which numbers, the range of numbers that it can cover. So if you consider the fractional number, in that case dynamic range is decreased but resolution is increased. But in case of integer, dynamic range was higher but resolution was lesser. Okay. So there one comparison is given, floating point. So this was the discussion related to floating point. So for floating point, um, representation, there was mantissa and exponent. Okay. And in both mantissa and exponent, sign bits are there. So there are two sign bits in floating point, one for mantissa and one for exponent. Now let us say we keep 23 bits in mantissa, okay, and 7 bits for exponent. So 23 plus 7, it is 30. Then plus 2 for sign bit. So all total is it is 32 bits. So in that case, the smallest number is what? It is 0 is the sign. Okay. Smallest number in magnitude will have the representation that this one. So 0.1. Okay, 0.1 because maximum values of minimum value of mantissa is half. Okay, 1/2. So it is 1/2 means 0.1. Okay, 0.1. So 0.1 and rest all bits are 0. So this is the minimum values of mantissa. Okay. So here sign is not considered negative. Here sign is positive. But in case of the exponent is negative. So that means it is 2 to the power of some negative value. Okay. Say 2 to the power here how many bits are there? It is 3, 4, 7, 7 bits. So its value is 2 to the power -7. Okay, 2 to the power -7. So here actually it is showing 2 to the power -127. Why it is so 2 to the power 127? 7 bits. What is the value of 2 to the power 7?
Sir, 128.
Yes, so 128. So actually it is not 2 to the power -127. Actually it is 2 to the power 7 minus 1. Okay. So uh, so 2 to the power 8 minus 1. 2 to the power 8 uh, 2 to the power 2 to the power 7 how much? What you told?
Sir, I told 2 power 8 is 128.
2 to the power 8 is
No, sir, 2 power 7. 2 power 7 is 128.
yes. So it is that's why it is means whole value of this exponent. So if your number is 1, there are seven ones. Okay, so 7 1 means 2 to the power 7 minus 1. Okay, so 2 to the power 7 minus 1 is 128 minus 1, isn't it?
Yes, sir.
Okay, so so 2 to the power 7 minus 1 is 128. Then minus 1 is the this thing number. And since sign bit is negative, so that's why it is minus 127. So it is actually this way it is represented. It is actually 2 to the power 7 minus 1. So in binary it is you see that how much value it's it is 10 to the power minus 38 in decimal, 10 to the power minus 38. So this is the lowest number. uh, so 0.5 is the mantissa and sign bit is uh, and the exponent is this one, 2 to the power minus 127. So here we uh, mm, so what is the largest number for this case? It is uh, Again, mantissa and exponent. Mantissa is 0 point, then all bits are 1. Okay, so it is 23 bits. All 23 bits are 1, and exponent is positive number. Okay, so sign bit is 0 and remaining 7 bits are 1. So in that case, this is the magnitude. Okay, 1.7 into 10 to the power 38. So the same word length, 32-bit word length for fixed point and floating point. See the difference. Okay, see the difference. It here in the case of floating point, it goes up to 10 to the power 38. Okay, uh, means 10 to the power minus 38 to 10 to the power plus 38. So all total it is 10 to the power 76 is the dynamic range. Okay, but resolution is different. But uh, what for this fixed point, the dynamic range is far lesser. Dynamic range is only of up to the order of how many digits it is, uh, 3, then 7 digits in decimal, and here up to 38, uh, 30, it goes up to 10 to the power 38. So a lot of difference is there in the dynamic range for fixed point and floating point. So that's why the floating point representation has more advantage over fixed point. But um, resolution is different. In particular, we have fine resolution for small numbers and coarse resolution for large numbers. Okay, in floating point representation. So if you increase the dynamic range, the resolution will increase, means decrease. Coarse resolution is value is large, not small. But in small numbers you will get good resolution in case of floating point. So this is what about the this number system. And one special case is there, that if you use mantissa 0, okay, if you want to represent 0, number 0, okay, so in that case mantissa should be 0, okay, but not the exponent. एक्सपोनेंट को हम लोग जीरो नहीं कर सकते हैं, because it is 2 to the power 0, that means the number becomes 1. So mantissa should be 0. Okay, then some IEEE standard format is there. So you see it is 32-bit system. Okay, so first 0 bit is meant for sign, and remaining 1 to 8 bit is for exponent. First exponent is written, and then mantissa for 9-bit number 9 to 31. Okay, so I'm not going to the detail of it. So just I have given you the idea, okay, how the number systems is, how the number systems of works. Okay, then let us go to the to some topic related to truncation. Okay. So just 4 or 5 minutes I require to cover this topic. That truncation means what? Initially we have BU number of bits. Okay. Say for fixed point, we have BU number of bits. Now we want to reduce it to B number of bits. So uh, we are not doing quantization. Quantization is different issue. Truncation here takes place before quantization. So truncation means just reducing the number of bits. Okay. So number of bits is BU, okay, and including the sign bit or whatever it is. Okay. Now it reduces to B. So what is the truncation error? That after uh, so B is less than BU. Okay, so for example, if X represents the sample of an analog signal, then BU may be taken as infinite, very high number of large number of bits are considered to represent X. Now, suppose you quantize it to say 3 bits. So you have divided the whole range into certain levels, okay, depending on the number of bits. So this is the process of quantization. So here I have written that truncation means reducing the number of bits after quantization. Okay. So say earlier one number was represented with very large number of binary digits. Now it is reduced to say fewer number of digits. Say earlier it was 8, it represented 8 bits, now it is represented to 3 bits. So we divide the whole dynamic, the range of the signal by some levels. Okay, and at every point, at every point of the analog signal, there is actual value and there is quantized value. So quantized value is taken depending on the level at which it falls. Okay. So whatever the analog values are there in particular level, they will be all assigned to that particular quantization level. So uh, actual value is X, and after quantization the value is QTX. So definitely there will be some error that is called truncation error. So that means you reduce the binary bits, then it occurs, this error occurs. So if say uh, for positive numbers, okay, positive numbers, what is the difference in their resolution? The resolution is 1 by 2 to the power b. Okay, that is the LSB. In case of this quantized number, in case of unquantized number, it is it is uh, it is BU. Okay, so B is less than BU. So let us say before quantization its number was 5 bits, and after quantization is 4 bits. So the difference in the resolution is 1 by 2 to the power 5 minus 1 by 2 to the power 4. So it is negative value. If you see, this number is smaller, 1 by 2 to the power 5 is smaller, than 1 by 2 to the power 4. So uh, that's why it is negative. Now, in case of uh, this sign magnitude representation, this in case of negative numbers. Okay, in case of negative numbers, this was for positive numbers. The quantization error is negative. Truncation error is negative in case of positive numbers. But truncation error is positive in case of negative numbers. Because negative numbers, what happens? The numbers is, the quantization is, resolution is minus 1 by 2 to the power 5 and minus 1 by 2 to the power 4. So difference is positive. Okay, so you see it is 1 by 2 to the power 4 minus 1 by 2 to the power 5. Okay, so this is there. So the truncation error for sign magnitude representation, it is from minus 2 to the power minus b minus 2 to the power bu to plus 2 to the power minus b minus 2 to the power bu. This is the truncation error, range of truncation error. And what is the uh, quantization error? Quantization error, you know that uh, half of LSB. Okay, so half of LSB means, because you know, if you look into the figure, that if uh, some analog quantity is falling, okay, at the middle of the level, individual level, then what binary value we will assign? Either this lower one or upper one. So we decide that which one will be taken, either the next number or the previous number. That means, say one number is existing between 100 and 101 in analog domain. So we will see that which value will be assigned, 100 or 1001. Okay, if it is situated at the middle, so there is some error regarding that. So that error is the half of the LSB. So LSB is 1 by that value, okay, 1 by that 2 to the power b, 2 to the power bu. So that is half of that. So you have studied in digital communication that PCM, pulse code modulation. You must be knowing how this quantization error is calculated. So this is the quantization error. Okay. So minus half LSB to plus half LSB. So here, so just up to this, I wanted to tell you. Now, next next class we will discuss on the last topic of this module, that is quantization of filter coefficients. It's a not very big topic, but it is there's some detailed studies there. We just touch all these topics. So now today I finish here.